My name is Eliza Good, and I work at Olympic National Park. Thank you all so much for being here today, and especially thank you to our speaker, Dr. Andrew Fountain. Dr. Fountain is Professor Emeritus at Portland State University, and he has been studying glaciers since 1980. His research made headlines in the past year with the prediction that the Olympic Peninsula glaciers would no longer exist by 2070. And he'll be sharing some of that research with you tonight. At Olympic National Park, together with friends like North Olympic Library System, Port Angeles Fine Arts Center, Discover Your Northwest, and Washington's National Park Fund, one of the ways we're reckoning with the loss of these glaciers is by forming a community of artists to create original poems, paintings, songs, dances, and more to honor the glaciers, and we call this project Terminus. There are so many ways to bear witness to the effects of global climate change, from science to art and so much more. As you listen tonight and perhaps visit the Terminus exhibit over at the Port Angeles Fine Arts Center, I hope that you'll feel empowered not only to face the dire truths, but also to not turn away from beauty. We live in a beautiful place and a beautiful world, and it's also a changing place. I hope you keep walking in the forest and sitting by the water and loving the places you love, and then try to do something with that love. I'll now turn it over to Dr. Andrew Fountain.
Pleased to be here, and thank you for the invitation to be part of the Terminus Glacier Memorial. One thing that I was thinking about when I was coming up here, I live in Portland, Oregon, is that on my honeymoon, we hiked to the Blue Glacier. So that has a little bit of relevance for me. Anyway, so we've been looking at glacier change actually across the Western US, and this, the Olympic Peninsula is part of that project, although we've been focused on this for the past couple of years pretty intensely. And I just want to say it's not just my work, right? It's work of a lot of people that worked with me on this, students and other professionals. Brian Menenos, for example, from University of Northern British Columbia, and then some other students here as well. So this is our cumulative work. You might not realize this, but the Blue Glacier has been well known in the scientific community for a long time. In fact, in the early 60s, it was, I should say, the early 60s, that's right. It was considered to be one of the glaciers that should be monitored. And one of 9 glaciers here. The northernmost is the McCall Glacier up there in the Brooks Range. So this has been kind of on the scientific radar for a long time. And in 1955, Dick Hubley from the University of Washington started doing work here, looking at the how weather changes the melt on the glacier and what are the particular physics connecting the atmosphere to the snow and how the snow melts. And then soon after that, a bunch of people in a collaboration between Caltech and the University of Washington were studying the glacier in a large number of ways. And what you probably don't appreciate here are these people kind of brought glaciology out of the kind of the geologic domain of there's glaciers and here's how it affects the landscape, to the geophysical domain where they actually make predictions of how glaciers flow and how water flows through glaciers and how glacier dynamics can be modeled. So, and then, like, for example, Phil Church there, he developed a snow sampler that the Forest Service now uses across the country. And Austin Post at the bottom there, he developed this basic theory of tidewater glaciers and how they react in southern Alaska. And these were all young people working on the Blue Glacier during the 1960s. And Ed LaChapelle, who became an avalanche expert, carried on fundamental studies on how do you measure the mass change of a glacier. What we're interested in is how much mass it gains and how much it loses. The advanced retreat is interesting, but that's noisy because it takes a while, as everybody knows, for mass to change on the glacier and the glacier to react. So we need to know how much is input and output to really understand what's going on with the glacier. And he led a lot of those early studies. So this is really kind of the proving ground for a lot of techniques that we still use in glaciology today. This photo, this is how they got to the glacier. They take a fixed-wing aircraft and land on skis on the upper part of the glacier on the snow dome. And this was actually featured in a Lassie movie, because what would happen is, this is Bill Fairchild. To take off, he didn't really have long enough a runway, so he flew out and just dived off the ice fall, getting airspeed so he can take off. So you can check out that Lassie adventure where I forget exactly what happens, but I think the dog gets hooked and taken up the air or something like that. Anyway, I leave that to you. So these are just some pictures of the kind of studies they did. This is a meteorological tower that you're trying to understand what's happening in the atmosphere and how that affects the snowpack. That's not trivial to erect in a snow-covered region. Here they actually had tunneled into the ice, and they're trying to measure the deformation of the ice right at the bottom of the glacier and how glaciers move. And if you've ever tried to dig a tunnel in ice, it's cold, messy business. Because it just, all the ice gets on you, then it melts, and it's like being in a snowstorm all the time you're in there. And there's one experiment that's continuing to this day. Ed LaChapelle put out these triangles that are purposely twisted so they look, unusual. And he spread them out on the glacier, recording where and when he put them, and for future generations to find them later, lower down on the glacier. And hopefully they record where they found it and what time. And then they'll know how long it took that triangle to get there and where it came from. So it tracks not only flow rate, but also tracks flow direction, what part of the glacier flows to what part. So we inventoried, all the glaciers in the Western US. In fact, we just published on that like last week. And the Olympic Peninsula is part of that. And, the thing is, well, how do you inventory, how do you map glaciers per se? And here's an example, the Humes Glacier. I think we'd all say, oh yeah, that's a glacier. And when I look at it, I see the accumulation zone where more snow falls in the wintertime than melts off in the summer. So that becomes the recharge area for the glacier. And then you have the ablation zone. Ablation is mass loss in all its forms, like melting, sublimation, calving. When you weld, you're ablating the metal. This is the ablation zone, where more mass is lost than is gained by snow. So the glacier is fed from here and flows down that way. But that's based on 100 years or 250 years of research that I can tell you that. But back in the day, when they were first looking at this, how do you define a glacier? And at the Philosophical Society of Washington, which still exists today, they meet in the Cosmo Club once a month. And at that time, they had this symposium, or I should say an annual meeting. This is 1884, and they had a little symposium, which I think they probably hung out after the meeting and kind of talked among themselves about what is a glacier. And the luminaries of that era were talking about that. So Israel Russell, who did a lot of work in Southeast Alaska, and developed actually a kind of inventory of where glaciers might be in North America. He wrote an article on that. He was there, he talked about it. And his initials, Icy Russell. So at the time, he's this glacier expert. And I am still trying to figure out, was that known as a kind of a joke at the time, or is it just me? And then Samuel Emmons. He was part of the first scientific expedition to discover glaciers in the West. Clarence King went down to Mount Shasta and discovered a glacier in the fall of 1871. But part of his party was Samuel Emmons, who he sent up here to Mount Rainier. And Emmons said, "Oh yeah, there's glaciers on Mount Rainier," and that's the Emmons Glacier, if you know the area. That's from him. And then you have G.K. Gilbert, who is the father of American geomorphology. So all these people are kind of figuring out, well, what is a glacier? And it's stunning to think, just from our modern perspective, that one argument was, well, it's just the ice part. That's a snowfield up there. And we don't really talk about that. This is really the glacier part. And other people were saying, well, no, I think it's the whole thing. And then it was like, well, okay, but do you really want to include this upper part here? So there's this whole discussion going on about what a glacier is. And at the conclusion of the symposium, it said, no conclusion was reached. So I don't know when we exactly decided on the definition. And here's where it's important. So if you're trying to inventory glaciers, well, where are they here? You know here, this is a moraine, and the glacier was there at one time, but that doesn't mean that is a glacier now. Well, one thing we can see is here's some ice, right? So we know it's been there a while. In this image, we can't see it moving, but this color of the water means there's glacier flour in it. So the glacier has been moving, carrying along rocks and grinding it against the surface, creating a fine powder that the streams then transport to the lake, and that's what you see. So you can say that's probably a glacier. And these other features here, well, what are they? Well, I can tell you that this looks like there's ice, but this isn't moving. Another way we can tell that it's moving is from crevasses. So the definition then for glaciers is perennial snow or ice that moves. So if we see crevasses, so thought it was a question. Okay, good. So if there's a crevasse, it's moving. It's the stress and strain of the ice that's causing the crack to form. And if it has ice, it's perennial, because it takes roughly somewhere between 10 and 20 years for snow to develop into ice. So that would be considered perennial. And for our work, if we saw crevasses, we called it a glacier. If it was on all the aerial imagery that we've seen, which can go back decades. So that would be considered perennial. So what we did was we used aerial photos, which are free from the U.S. Department of Agriculture. They fly the country every several years. And if the imagery is any good, because sometimes there's seasonal snow covering everything, we can download that and then trace the outline of the glacier. So you can see this is obviously a glacier because of the crevasses. You can probably see that here. This one, we decided it wasn't, because I think this one didn't appear on previous imagery. So this is just seasonal snow. So this is kind of what we did in the Olympic Peninsula. So just to kind of give you a sense of what's going on, and I'm a little leery about these kind of graphics, because my sister went to a science talk once and she said, that guy showed me so many graphs, my eyes crossed. So I'm always a little leery about how many graphics to show, but this is the way scientists think, and we like having pictures to help us out. So this here is the number of glaciers, and this is their average elevation. So the average elevation, if you know, the peak of this is around 1,800 meters, which is a little bit less than 6,000 feet. So this is kind of where most of the glaciers are, and they're all pretty small. This kind of funny axis actually is logarithmic. This is 10 to the 0, 10 to the minus 1, 10 to the second. And so it's just easier to clump the bars this way. But the point is that most of the glaciers are pretty small, a little less than 25 acres. And the largest is a little bit less than 3.9 square miles. So relative to Switzerland, these are really small glaciers. The blue, of course, being the largest. And as typical up here in the northern hemisphere, they face north, because you have the sun beating down on more intensely on the south side of the mountains and on the west side. So the glaciers tend to face north and occasionally a little bit east. Just the opposite in the southern hemisphere. They face south. So, you know, the area change of the glaciers is linked to elevation, as you can probably imagine, right? It's colder higher up, gets a little bit more snow higher up. This is fractional area change. So if there's no fractional area change, 0, it's 0. But if it's -1, that's 100%. So the glaciers disappeared. So this is 40% loss here, minus 0.4. And we do it this way because if we did actual area change, the big glaciers would change a little bit, but that's a huge area. And the little glaciers would change a little bit, and that's a teeny area. So it's hard to relate those. So it's easy to do it relative to their own area. So that kind of normalizes it. So you can see that there's less glacier change higher up, which is to be expected. But my point in this graph is actually different. You can see how scattered those points are. It's not exactly like they line up on that trend line there. And the reason is you got glaciers that are really climatically sensitive, and you got glaciers that are less sensitive. And this is a case in point. We have 2 unnamed glaciers here in the park. And here, this one's sitting in this bowl. And it's nicely shaded, you know, from the south and the west. The shading will get cover more of the ice if, you know, as the sun moves down through the rest of the day. So this is kind of nicely shaded, and also it's in a bowl. So not only does this glacier get direct snowfall, it also gets avalanching. So yeah, so if the climate warms a little bit, this won't melt as much because it's getting extra snow. Unlike this glacier. Here, this glacier is totally exposed, hardly any shadows, no cliffs to provide extra snowfall. It just gets what it gets directly from the clouds onto the surface. So this would be considered a more climatically sensitive one. And this one here is less sensitive. I don't want to say insensitive, just less sensitive. So here, you know, you might have this guy changing only, say, 20%, and this guy here changing like 50%. And it's because of their topographic setting. So not all glaciers are kind of created equal because of that. So here are the results of the imagery that we've had. This is, for those of you who know something about glaciers in the park, this is the Rich Spicer report, who did the first inventory of the glaciers in the park. And we've had imagery for those next 3 years. Why did we stop in 2015? They didn't have any good imagery since then until I think like 2019 or 2020, something like that. But by then we had already been through our study and just haven't been able to catch up. So same funny x-axis on the size, But the point is, you can see the glaciers are getting smaller and smaller as the peak of those bar charts move to the left. And we're getting, you know, obviously small, less and less big glaciers at the same time. So I've always found that charts like this, tables of numbers, it's always an audience favorite. So, and I want to make sure that you guys enjoyed one as well. But the point is, here is just the largest area. This is Blue Glacier, goes from about 6 square kilometers to about 5. The mean area of the glaciers are about half, 0.18 to 0.10. The total area, 45 square kilometers to 25. So a little bit less than 50%. 35 glaciers have disappeared in more recent times, not back here. And then we've estimated the volume of the ice, and it's almost half. So you lost half of the volume since about 1981. To put this kind of in context for the Western US, so this is what we've been working on. And these are pie charts. So this shows the red is how much has been lost. So this is 100% back in 1981. And now it's half of it's been lost. And you can see the different areas of the country. These funny areas, these are, since we're doing the work for the Forest Service, this is different regions that the Forest Service has divided the Western US into. But you can see what really stands out is Washington. Only lost 25% for the whole state. And you can see I added that little one just so you can see what the Olympic Peninsula looks like relative to the state of Washington. And the reason is here that because the glaciers are higher, particularly Mount Rainier, you know, there's more glacier area on Mount Rainier alone than there is in the rest of the U.S., rest of the Western U.S. Not Washington, but the rest of the Western U.S. It's like a 1 or 2 square kilometers larger, and those glaciers aren't changing quite as much as everybody else. Plus, you have the relatively high glaciers up in North Cascades as well. So in contrast, the ones here in the peninsula have really retreated quite a bit. And I'll talk about why that is in a minute. But that kind of stands in contrast. In a sense, what's happening here in the Olympic Peninsula is more similar to most of the country and not similar to the rest of Washington. And we also, you can see here, we track perennial snow fields as well as glaciers, more for hydrological purposes, since they do supply water to high alpine streams. But that's not the point of the talk here. So this is a graphic from the World Glacier Monitoring Service out of Switzerland. And this just shows globally the mass change of all the glaciers and ice caps. So this would include Iceland. It does not include Greenland or Antarctica. So it's Iceland, it's Europe, it's the Western US, Canada. And you can see it has been decreasing. So our results here are consistent with those results seen worldwide. Yeah. That's cumulative. Thank you. Yeah. So this is like a bank account. Every year you add some or subtract some. And well, if the glaciers were in equilibrium, it'd just be a flat line. Yeah, but since they're constantly losing mass, it's going down. Yeah. So some pictures of what's happening to Anderson Glacier over the last 100 years. This is a sequence of photographs, and you can see, I recommend that you'll want to look here, but look how things change up here. We can against the bedrock. So you can see here how the glacier just kind of deflates, and the bedrock becomes more and more exposed. Yeah, so big change between 82, which is basically the start of our study, and 2004. And then this is the last one. And Bill, you gave me this photo from Byron. Yeah, so this has really changed a lot. So this is what we're seeing here in the Olympic Peninsula. This is clearly an extreme case. Not all glaciers certainly have disappeared. But a good one to track actually is the Blue Glacier, because it's the largest. There's been a lot of interest in it. A lot of people have taken photographs of it. We can track its change with time, and you can see how the glacier changed between those two years there. And because of people taking pictures, we can see that the glacier in the early 1900s was kind of steady, then it dropped, and then it kind of became steady again. In fact, it increased a little bit in the 1970s, and then it started to drop off the map here. And this is very typical of glaciers in the Northern Hemisphere, particularly those here in the Western US. This is called the mid-century cooling period. And this is relatively well known, that the glaciers paused a little bit. They kind of just didn't, what am I trying to say there? They didn't retreat very much. And in this case, some glaciers like Blue, because Blue is very climatically sensitive, actually increased a little bit, advanced a little bit, and then decreased. So this is well known here, this mid-century cooling. So this is what's happened to Blue Glacier. This is typical of glaciers in the Western US. And what are the reasons for that? So there's a lot of information packed in here. Again, we have the same graphic here. This is Blue Glacier, the dots I just showed you. The gray line was the model that we developed to understand how the mass of the glaciers changed. And this is the weather in terms of precipitation and temperature. The red, solid red, is winter precipitation. And you can't really see it, but the dashed red is, excuse me, the red is winter temperature, and the dashed line is summer temperature. And the gray here is precipitation, just winter precipitation. We don't care about summer precipitation. So the immediate thing you can see here is it's warmed. The glaciers retreated. What about the precipitation? There's no trend there. The precipitation isn't getting more or less. It's kind of staying the same, but the glacier is retreating. So it's got to be temperature. That's what's causing the glacier to lose so much mass and retreat. So that's kind of on a century scale. But on a decadal scale, you can see here that that you have, like during this period, you have not much snowfall, warm temperatures, warm winter temperatures, you have decrease. And conversely, you have cold period, cold winter, lots of snow, glacier increases. So this is, so on a decade-to-decade basis, you see how the differences in temperature and precipitation control things. These dashed lines, I took out of the literature. This is not something I invented. And this is the Pacific Decadal Oscillation, PDO. Have you guys heard about this? Oh, you're really affected by it here because you're so close to the Pacific. Basically, it's sea surface temperatures. And this guy at the University of Washington developed this way to average sea surface temperatures in a way. And the warm phase is when the water is warm near the coast, and the cool phase is when it's cool against the coast. Took me the longest time to figure this out. Is, your eye looks at this and says, oh, cold. Why is it the warm phase? Well, it's warm because it's up against the coast here. So the ocean has this natural cycle of warm and cool periods. Not exactly always on time, but every 20 years or so. And that's what these are. This is the shift between a cool phase, warm phase, cool phase, warm phase. So you can see cool phase, nothing happening. Warm phase, glacier retreating. Cool phase, everything's great. Warm phase, it's retreating like crazy. Cool phase, it's the effect of climate warming. The cool phases of the PDO aren't benefiting the glacier like it used to. And that's kind of one of the scary things if you like glaciers. So what about the future then? Well, this is a graph of climate over Mount Olympus. And the red here, again, is temperature, monthly temperatures. So this is January through December, monthly temperatures. So you can see it's warm in the summer, makes sense. This is maximum, average minimum. And then the bars are precipitation. Again, like better than most people, really, really wet in the winter, pretty nice during the summer. The deal is the winter temperatures are pretty warm. They're only a few degrees below freezing. And that's what's critical here, and that's what's different here versus in the North Cascades or on Mount Rainier. So in a normal climate, during the wintertime, cold temperatures, you have precipitation, it's snow builds up, nourishes the glacier. Summertime, it's really warm. It melts off most, but not all the snow, because that's what ultimately nourishes the glacier. And you have some ice melt, and you have runoff. But in a warming climate, particularly here on these glaciers, this cool temperature gets a little bit warmer, even closer to freezing. So what happens is during the winter time, it doesn't get that cold. You get some snow and you get rain. Rain doesn't do anything for the glacier. You want the snow. So you have less nourishment in the winter. In the summertime, it's even warmer because it's climate warming. So this is melting like crazy. So now it's a double whammy. It's not just summer warming that melts the ice. It's winter not nourishing it as much because you're getting more rain and less snow. So you don't need to have differences in snowfall, differences in precipitation. You just need to have differences in the phase of precipitation, rain versus snow. So the glaciers here in the Olympic Peninsula get this double whammy of less nourishment in the winter and more loss in the summer. Yeah, that's right. That's what I was trying to remember. Yeah, and because they're at a low elevation, because you used to get tons of snow coming in, just blanketing the mountains. Because you're a lower elevation, you're way warmer than those ones in North Cascades or in Mount Rainier. So you're vulnerable, and this is going on. And this is kind of the basis of this map that Ann Nolan and Chris Daly produced a number of years ago for the Northwest, looking at snowpack temperatures and what they called snow at risk. Under that idea of warming winter temperatures would cause more rain to fall and less snow, they mapped that for the Western US. You can see lots of Oregon, snow at risk. They're the one, this is the snow that's going to be melting off or not accumulating as much because there'd be more rain. And guess what? Here we are in Olympic Peninsula, same deal. Low elevation, warm snowpacks. You're going to get more, as with climate warming, warmer winter air temperatures, and you're going to get less snow. And the snow that's there will melt off relatively quickly because of its temperature. So this is the I wish I had a better end slide. But this is what we've done and what Eliza referred to in the beginning. We borrowed this model from our colleagues in Canada that looked at glacier change in Western Canada, and we modified it for use here on the Olympic Peninsula. And using the current scenario of business as usual with climate warming, I drove my car up here. You know, I'm part of the problem. Based on that scenario, where we don't do anything, the area of the glaciers will basically go to zero by about 2070. And the volume the glaciers get so thin that, you know, you don't see much thick ice by 2060. Under modest scenarios, that if we do a little bit, you know, greenhouse gas mitigation, but not enough, we just do a little bit, we'll probably go out to maybe 2090, maybe 2100. So that's kind of where we are with that. It's just not looking good. The glaciers on Mount Rainier will be a lot smaller, but they're going to also be a lot higher. You're not going to be able to get to them as easily under this same situation. But because it's so high on that mountain, the temperature will still be cool enough high up. It's these low elevation glaciers that are present here on the Olympic Peninsula that is the reason why they're so vulnerable. So I'll leave this up here and I'll take any questions. Thank you.
The question so that the people at home can hear.
Okay.
Any questions? Couple. How old is some of the ice in glaciers?
Oh, good question. How old is some of the ice in the glaciers? I don't know, but I can give you an educated guess. Based on the time it takes the ice to flow from the top to the bottom, maybe not as old as you think. Something like Blue Glacier, I don't know, maybe 400 or 500 years, I would think. The reason is, unlike Antarctica, where you know the ice can be hundreds of thousands of years old, they just get a little bit of snow, and it's really thick, and it doesn't melt off much. Whereas here, the turnover rate is huge. You can have 30 feet of snow, and you can have 30 feet of ice melt. So it's really moving through the system rapidly. It's a fast-moving ice river compared to Antarctica in that sense. Yeah.
Curious, whenever you're area retreat maps, it all seems like second row of acceleration in the retreat. And so it seems like the slope steepening and how good. And when I look at the future maps, it's kind of like a steady fight that. Is there any risk that your future forecast maybe wants to do?
Yeah, I see what you mean.
Historically, it's like the slope was getting much steeper and things were accelerating faster over the last 4 years, if you will. And so, in your historical, and then now.
Oh, I see what you're saying. Yeah. So what's happening is the glaciers are retreating into more favorable climate, so to speak. Yeah. So they become less climate sensitive. You know, that's part of it. Yeah.
So back to the cave ice.
Yeah.
The oldest ice at the bottom of the accumulation zone, or is it at the terminus?
It's at the terminus of the glacier. Because the flow path, if this is the glacier, this is the top of the glacier, this is the terminus. The flow path for the snow at the very top actually is kind of along the bottom of the ice out to the terminus. Whereas if you're halfway down, it just sort of goes into the ice and then comes right back out again. So there's kind of flow lines of age, if you will, through the ice. Yeah.
Not like that where there's like the boulders on the bottom. There could be mixing in places so that the
No. Yeah, it's stratigraphic, but there's no overturning in the glaciers, so it's all kind of like flow lines that it is oldest on the bottom and least on the top. But that's a good point for the reason that when they drill ice cores at a flow divide. So like if you're going to drill at Blue Glacier, you'd want to drill between the White Glacier and the Blue because there's a flow divide. So the snow that falls right on top of the flow divide just goes straight down. So reconstructing what the time is of that ice as you deepen is very simple, whereas in a glacier that's flowing, it becomes more complex. Yeah.
What does that mean? For more ecologically.
Oh, climatically sensitive. Yeah. Well, I was talking about the topographic effect on the glaciers. That if you're flat and you're exposed to the sun and you get direct snowfall, you are more climatically sensitive. Whereas if you're in a bowl with lots of shadows, then the shadows don't prevent the ice being melted too much from the sun, and the bowl allows more avalanching, which nourishes it more. A little bit, but not as much. No, it's got the big snow dome up there that is very exposed. The lower part of the glacier is kind of shadowy, but that's not what's nourishing the glacier as much. Yeah. I'm sorry, I'm not repeating the question, am I? I forgot. I see I get into it, right? And so I'm sorry, how do the glaciers affect the rivers? Let me answer what I think you're asking, and you tell me if I'm on track. There's two things to consider. One is just on an annual basis, glaciers really feed the rivers a lot during the summer, and they prevent those rivers from going into drought versus a river or a stream that's in a basin without a glacier. Because if you don't get any rain, you're not going to have stream flow. But with the glacier, you always have water. So for that reason, some of the trading posts along the Silk Route in Western China were located on glacial rivers because that was a constant source of supply. With glacier recession, those rivers are going to be more and more vulnerable to drought. And of course, whatever species of animals or plants, for that matter, along the riparian zone will be more vulnerable to those changes as well. So that's something that will happen.
In the world, are there certain spots that don't meet your graph? There's some growing, and you don't really know probably know why, but
so are there any areas in the world where there are growing glaciers? Yes, and I know why. Well, actually, there's two areas that come to mind. One is really close to here, Mount St. Helens, the Crater Glacier. Yeah, but that's because you remember that eruption? But you heard about it. Yeah, so that created a perfect snow gauge because the mountain blew up and it's a north facing crater, and the snow is coming down off the sides, filling an area that didn't have any snow. So it's creating a new glacier. Then at the same time, there's a lot of rock coming in. I think roughly half of the ice mass is rock in that. So that's why that glacier is advancing, but that's not really the thrust of your question. There are glaciers advancing, and the time being in part of the Karakoram in the Himalaya, and that's because of increased the way the atmospheric circulation is. It's increasing snowfall in that area. They're not increasing a lot, but a little bit. But that's in contrast to everybody else. So it does happen. The ones in Scandinavia, they didn't start retreating until the 90s for the same reason. There was just a lot of moisture being carried in off the Atlantic for atmospheric circulation reasons. And then as soon as that stopped, then the glacier started retreating like crazy.
Someone in the chat asked, do you foresee that we will start utilizing snow machines for some other tech to help our glaciers?
Do I have to repeat that? No, okay. Did everybody hear that? You know, it's not energy efficient to do that. You're kind of creating more of a problem than you're solving. But there are people trying, particularly in Tibet, I think it is, maybe northern Pakistan, trying to create what they call ice tupa, where they in the wintertime they pour water over an area and create a large mound of ice that then melts in the summertime to feed their streams. But I don't know where they get their water from, but it's really small. It's not going to feed streams a lot. And we definitely cannot do that here in the West, because in the wintertime, you start pouring water on something, and then we get a snow dump. And then it doesn't get cold enough for the water then to freeze. So it's just, for us, that's not a viable solution. So. I'm curious about the triangles. Has anybody found them? Bill, you found them?
Yeah, so we had, I believe, 5 or 6 of them. And I found one, I think the most recent, I found one about 4 years ago when we were up there. And we have, I was actually just thinking about that, Andrew, when you brought that up, because I thought maybe we should, you know, we do have 5 or 6 that have been found, and we know roughly where they were found, some precisely where they're found. You know, maybe we should throw that out there in a quick publication.
No, I totally agree.
Because, you know, I anyone wants to come to my office, I have one hanging on.
Oh, nice.
Where it started. We're kind of napped.
Well, it would be a nice memorial for Ed LaChapelle, you know, that his long-term experiment, something's come out of it, and we're not getting any younger, so.
I have a funny story about it, which is that one showed up in the mail at the park with a little letter saying, I'm really sorry, I found this a long time ago, and I drew it out and kept it, and I saw your talk.
Oh, nice, nice.
And here you go. And this is the year and roughly the month.
Okay, great.
So we're actually able to kind of go back and make an estimate of where we found it. We had aerial photographs from that year, and we could see the main route going across the glacier. And,
Oh, very good.
They marked it on a topo map where they thought they found it. So lined up.
Nice.
So that's
Yeah, this is equivalent to putting a message in a bottle and throwing it into to track currents. You know, this is exactly the same thing.
Like, how is it like when you lay it wet? Is that why it's a triangle?
No. He just made it into a triangle to make it look unique.
Oh, okay.
Yeah.
I thought, like, it was so, oh, I didn't know that.
Yeah. Plus in the snow, as it gets buried in the snow, it can also rotate itself. So that itself wouldn't work. Yeah.
they hold together.
So he did a good job.
A lot of our glaciers are pretty white all the way down, but in Mount Rainier, there's a few like Carbon Glacier that the rocks caved in on it. Does that slow things down at all?
Yeah, does rock cover affect the glacier mass or melt? Yeah, you bet. If you have an inch or so less on this snow or ice, it actually accelerates the melt because it's dark material and it warms due to solar radiation. More than an inch, then it begins to insulate. And Rainier, has some rock, like this, and the melt rate on those under that kind of rock is like inches per year. So that's one of the reasons why there's less glacier change in Washington. Those glaciers, particularly on the north side, are just retreating so little compared to everybody else, partly because of that. Yeah. Oh,
That comes from forest fires and lands on to glaciers, that would be small.
yeah. So does smoke from forest fires affect glaciers? Yes. Well, there's this whole field of study on black carbon. Black carbon is a very effective absorber of solar radiation, it's like 99% or something. Whereas clean snow is like 10%, right? So that reflects most of it. But anyway, yeah. So black carbon gets into the snow and increases its melt rate just because it absorbs a lot of solar radiation. And forest fires then have a feedback system, forest fires affect glaciers a lot by that. So, and then if the glaciers get small enough, you can have tunnels underneath the ice from the stream flow. And if the tunnel gets a little bit big, then airflow gets into the tunnel. And then you get huge tunnels under small glaciers, which then become fragile and then collapse in. So there's another way that the glaciers, particularly small glaciers, accelerate their retreat just through something like that. So as soon as you get small enough, things like the smoke and the water flow and all this really begins to devastate them quite a lot.
I don't know anything about it. I'm just curious. I know we do cloud seeding for like severe drought situations, and can we help precipitation manually?
Yeah. Believe it or not, I knew the guy that invented cloud seeding. When I was in high school, I met him. I used to work for him, actually. But the problem with cloud seeding is it's statistically hard to determine if you've affected anything because you can only seed those clouds that are about to rain or about to snow. How do you know they weren't going to do that anyway? Although there is some cloud seeding in places like Wyoming, but I don't know if it's that effective. I think the easiest thing to do would be just to reduce the carbon dioxide input. That's kind of a no-brainer. This geoengineering of putting sulfur dioxide into the atmosphere to make more clouds. It's like, really?
Places that have like racing stripes down
Right.
the middle.
Yes.
How does this stuff get there in the middle?
Okay, so yeah, how do the racing stripes form in glaciers? Those are called medial moraines. So it's where two tributaries come together and they're dragging rocks along with them, and then they kind of squeeze together and they form that ribbon. And in German, it's called Gesundheitsstraße. And it makes sense. Well, it's a safe place to walk. Yeah. The rocks. What?
But they're being by water.
No. The ice flow itself. Yeah, the ice is just moving down and carrying the rocks along with it. And then as you get lower and lower elevation, more and more ice melts, leaving this ribbon of rock on top of the ice. Well, from the tributaries, when they erode the side of the glacier, so this is the rock wall and the glacier is moving down this way. Yeah. Okay. Has there been any what?
Five thousand to Hubley, and how far was it down to bedrock?
You know, they've done ice radar on the glacier. They did early years drilling. I don't know if they've ever reached the bed. Bill, do you know if they've ever reached the bed in the drill? Whoops, that's,
I don't remember when I didn't remember that I didn't down to that.
yeah, yeah,
That was like. You probably have better.
yeah.
The only time they've ever estimated depth is based on the radar.
Radar, yeah. So nobody's drilled it. We don't think, yeah.
Well,
Huh.
5,000 feet up there. Something like that.
So the thickness of the ice that I'm aware of is like 250, 300 meters. It's building, yeah.
It's in that
Yeah, so almost 1,000 feet maximum. Yeah, which is pretty thick.
You put what would all of the countries that have the glaciers, what can we do to, retain them? We said lower our carbon footprint. If there, have you proposed things to, like, the United States?
Oh, we all know this stuff. Reducing global temperatures is based largely on greenhouse gases. So, I mean, that's what we got to do. And yeah, fossil fuels. Yeah. I mean, I don't think there's anything specific that one could do for glaciers. Yeah, that's right. That's right. Thinking about engineering solutions, in Europe, they've had a couple of demonstration projects where they've taken foil, a cloth, and covered glacier, and to reduce the amount of solar radiation and make it reflect more mylar. And then people talk about that as a possible solution, but can you imagine trying to stretch something a square mile and keep it in place on a surface that's melting with animals? Doesn't make sense. Anyway. Okay, well, thank you very much.